Okay, let's quickly go over what we learned from Monday. First, we talk about the how to add a transformer to the bus admittance matrix. So if a power network has all branches which are transmission lines, so the bus admittance matrix will be symmetric because any entry at the row I, column J will indicate the admittance between the bus I and the bus J. But when we have a transformer, we also need to identify the corresponding entries on the bus admittance matrix. So on Monday, we use this transformer representing the per unit values. So here we only need to know the ratio, which is 1 to A. So if all the voltages have been changed into per unit, so this A will be very close to 1. So if you think about then transformer can vary voltage by positive or negative 5 to 10%. So this A will change around 1, maybe from 0.9 to 1.1 for the most. But basically A will be close to 1. And we need to know the equivalent impedance of the entire transformer, and we change it to admittance here. Starting from Kirchhoff voltage and current law, we can have the two equations, and we write in this form, transform the voltage vector about the voltages on both sides to the current vectors on both sides. So we'll have 4 elements. So those 4 elements will be added to the bus admittance matrix. So one thing we notice is those 2 elements are very close, but they're not identical because A here is the ratio. So if this transformer is only just type changing transformer, not changing any phase of the voltage, so this A will be a real number. But if the transformer also can do a phase shifting, so A will be a complex number. So it will be will have magnitude around 1 and also with a little angle, depending on how much phase shifting the transformer can do. If it can change like phase by maybe 10 degree or 15 degree, so A will have a little angle. So A is not equal to the A star. So which means if you have any phase shifting transformers and also the transformer is doing the phase shifting right now, so the bus admittance matrix will not be completely symmetric. For the elements corresponding to the phase shifting, so you will have A versus V star, A star. But if you ignore the phase shifting, the admittance matrix will still be symmetric. So in general, the bus admittance matrix will be pretty much symmetric matrix, except for the elements corresponding to phase shifting. So when you want to form the data sheet for the power network, because we can use pi model to represent any transmission line, we can also have a pi model to represent transformer. So you just need to find out this transformation from the voltage current on one side to the other side. So compared to the standard model of transmission line, so we can identify those A, B, C, D. So if you draw the pi model, which will be like this one. So this is pretty much the admittance, right, divided by the ratio. Ratio is roughly 1. So this is pretty much the total admittance of your transformer. And on both sides, you have 2 admittances to the ground, so they are not identical. So it's still in the pi structure, but slightly different from the transmission line pi model. Okay, so this one is what we need to keep in mind. Oh, by the way, so there's some papers that talking about using, like, for example, the quantum computer to calculate power flow. Some paper assume the bus admittance matrix need to be symmetric. Okay. There's some other methods they need to assume the symmetry of the bus admittance matrix in order to decompose the matrix into blocks and for parallel computing. So if that's the assumption, those papers, they cannot give you accurate power flow solution. Then we quickly form the power flow equations. So the power flow equations is derived based on this general bus structure. So if the bus has a source, voltage source, we first convert the voltage source to the current source. Then we model the connections between this bus and all the other buses by the admittances. So if any physical connection is not in the network, we simply just make that the admittance matrix be 0. So if a transmission system, which is not a complete graph. By complete graph, I mean, so there's a direct connection between any two buses. So this bus admittance matrix will be very sparse. So if we assume a common power base, MVA base, so every admittance will be changed into a per unit value. So we start from the definition of the complex power at every bus, which is a product of the voltage phasor and the conjugate current phasor. Then we can have the current to be calculated by the conjugated complex power divided by the conjugated voltage phasor. And on right-hand side, we just take this structure, right? By utilizing the bus admittance matrix, we can form the right-hand side. So this is actually the most important equation in this section. So which is the basic form for power flow equation. So later we can have some other variants based on this equation. For instance, we only take a real part or only take an imaginary part, depending on we want to calculate EOQ. But all such equations, or we call power flow equations, start from here. So for the capital Yij, which is just the elements or entries of the bus admittance matrix, so by definition, for the off-diagonal elements, so that basically just a negative actual admittance. For diagonal elements, that will be equal to the sum of all the admittances connected to this bus. Okay, so this is a complex equation for each bus. So if I have n buses, we'll have n complex equations. Each equation has how many real variable? We have P, Q, V absolute, and also delta. So our goal is to solve all the 4 values, or if we don't know all of them, if we're given P and Q, we need to calculate absolute V and delta. If we're given P and absolute V, we need to calculate Q and delta. So anyway, for each bus, we need to determine the 4 values of those 4 real variables. But we only have n complex equation, which are equivalent to 2n real equations. So which means for each bus, we need to know 2 of the 4 values to make all equations solvable. Okay, so to talk about the power flow solution, so our goal is to determine all the 4 values for each bus. So there will be two popular methods solving power flow. One is the Gauss-Seidel method, the other is a Newton-Raphson method. So we're going to go over each of the 2 methods. As we mentioned, we need to know 2 of the 4 values at each bus. So depending on which 2 are known among the 4, so there's a multiple combination. There are 3 very classical combinations which are utilized by most of the method. Include those 3 classes. So the first class, we define load buses. Load buses means for substation, we know the power and also power factor, which means we know P and Q. Okay, but we don't know voltage, magnitude, and angle. So voltage magnitude may change with the system condition, and angle may also oscillate. But we allow those 2 to vary, but those will be the two values we need to calculate or determine for that type of buses. The second type is generator buses or regulated buses. For those buses, we know P and V. By V is here, we mean the absolute V. Okay, but we need to calculate the Q and angle. For instance, if I have a power plant whose power output is scheduled, the P is scheduled based on the the operator or the market. Voltage and magnitude can be controlled by the voltage controller. Then we need to calculate how much Q and also how the angle can change. So if we classify all buses of the system as generator buses and load buses, which is not enough, because you need to have another bus which can balance the power of the system at any time. So such bus is called a slack bus or swing bus. Slack bus, swing bus, we assume we know the voltage, magnitude, and angle. And the P and Q can be any value. So the P and Q just try to compensate imbalance of the entire network in terms of both real power and the reactive power. So the powerful solution method typically will find the values of the first two types. And when we determine the first two types and the last type for the P and Q can be calculated depending on how much P or Q is to be needed to ensure the power balance of the entire network. Okay. So use this toy system as an example. And so here, if we assume a bus 2, we know the P and the voltage magnitude. This is obvious, that's the PV bus. For this load, we know P and Q. That's obviously PQ bus. And for this bus, we only gave the voltage magnitude to be 1 without angle. But we can assume the angle to be known. Okay, so this one will be a slack bus. And the bus 3, we didn't give anything, but we assume no load at this bus, which means both P and Q are 0. So this is also PQ bus. So we have a PQ bus here, a PQ bus there, and PV bus. And finally, the bus 1 will be a slack bus, right? It will be V delta bus. Okay, so then this power flow problem can be solved. So if you ask about any other type of buses, yes, you can definitely define any other types. If you have some new device which may be able to control, for instance, power and angle, or maybe the reactive power and angle. Reactive power can be controlled by controller. Angle may utilize some control system which is called phase lock loop, which can track the angle of that area and to adjust the angle. That is the typical technology we utilize to construct some angle or phasing for like inverter-based resources, like renewable solar farm, or maybe a wind farm connected through power electronic. Yeah, so you can definitely define any other types. But those 3 types are very important types for conventional power system. Then we talk about the Gauss-Seidel method. So Gauss-Seidel method basically just to find a root, find a single root from this nonlinear equation. So f can be any function. So to use this method, f doesn't need to be smooth. It can be any function. We just find any root which can make the equation hold. So the idea is very simple. We move one x to the left, and the remaining part of the f will be redefined as g. So this is the same equation. Basically, we just move one x to the other side. So the idea is we give it initial estimate. It can be any estimate. So usually we hope this initial estimate is not too far from the final root. Okay, so it need to be close to at least maybe one of the root. If the equation has many roots, not single one, then you give an error tolerance. Then you are ready to go to run the method. It basically just plug in that the initial estimate to the right, then you get left. Then you plug into the right again and get left. You just keep doing this. Eventually, you may have the x value doesn't not update much, and the change is less than the error tolerance, which means you can stop here. You just use the final result as a solution, estimate of solution. So using this example from the textbook, that's a 3rd order polynomial equations. It has 3 roots, 2 equal roots, and one, the third one is that's different. So if we want to solve this equation, we first just move the net x to the left, right? Then divide both sides by 9. So we'll have this equation. That's basically eventually just the same equation. Yeah. And then we can start iterate. If you give an initial estimate 2 and also error tolerance, you just keep iterate. Okay, so you see, so this indicate a gap, right? That need to be compared with the error tolerance. So when this one become smaller than 0.001, you need to solve. But when you iterate, you see this one can go up, right? So it seems to be in the wrong direction, but eventually a significant decrease and finally a get to the true solution. So if you visualize this process, for the transformed equation, the right-hand side is keep pretty much the nonlinear information, so which is the blue curve. The left-hand side, basically, this is just straight line. Okay, so the Gauss-Seidel method is equivalent to finding the intersection points between 2 curves, between nonlinear curve, which carry all the nonlinear information of the original function, and the linear curve. So because for this case, there's 2 intersection point. The first one is a tangent point, which corresponds to 2 equal roots, and the third one will be the third root. So we start from the initial guess. So we'll go through this process. We first plug into this blue curve, and then we which is equivalent to a moving up, following this vertical line. Then we plug in back to that nonlinear function again, which is equivalent to moving to the right, following a horizontal line. Then we plug in back the vertical line. So you just climb up, follow these stairs. So you see the gap or the distance between each stair. So that is actually correspond to the how much you update those values. So when you get to closer to the third root, eventually it will converge there. Okay, so that's why after next iteration, you get a good enough roots. So this is a visualization of a Gauss method. So which means this blue curve can be any function. It doesn't matter. So even you have, for instance, even the function is not smooth. It can be piecewise linear. You may still have hope to convert to the root if you close enough based on the initial guess. So we can ask a number of questions. The first is, can we converge to the root faster? Because for this case, it takes 9 iterations to eventually decrease the difference to the error tolerance. So what if we want to reduce the iteration? And the second question is, how can we find all the roots? Because for this case, from a iteration starting from a 2.0, we only get the root of 4.0. We didn't get to there's another 2 solution at 1.0. We didn't get those 2 roots. Third question is, does this procedure always converge? The last question will be, is there any other alternative way to write this nonlinear function? Okay, so in the following slides, we'll answer each of those questions. The first is, can we make iterations faster? There's one example on the textbook, 6.3. Okay, so this is the original Gauss-Seidel iteration formula. If we rewrite this formula, so on the right we add sk, which is the case estimate at the estimate at case iteration. We also subtract sk, right? That the right-hand side doesn't change, but this gave us a better idea. So what happened on the right-hand side is the original the current value of x plus the update of x. Update will be the difference between the GS minus the current s, right? So basically what Gauss method is doing is every time you plug in the value into the right-hand side, you actually update that value. So you update the value at the case iteration, and then by this much of change, so like delta x, then you get a new x. This is what the Gauss-Seidel method is doing. All right, so it's very naturally we can add some maybe coefficient to adjust the speed of updating. For instance, we can introduce acceleration factor. The only change is we just multiply the update by alpha. So if we make alpha, for example, 1.25, which is increasing the step by 25%. Okay, so each time, so we calculate the update, but we don't apply this update directly. We multiply this one by a factor. If the factor is bigger than 1, we actually update at a faster pace. So we still use the same case to visualize what happened. You see right now, each time when you update from initial estimate, we start from 2.0 as our initial estimate. So we still draw the vertical line to intersect with this blue curve at this point. This is exactly the same. Then when we draw the horizontal line, we don't stop. We don't stop at the magenta line. We actually go further. We go about 25% longer beyond that line. Okay, then start from this point, we go up. Similarly, at each iteration, we go beyond that straight line about 25%. Then we go up. So you see, we are taking bigger step to iterate in the same direction. So if we take this alpha value after 5 iterations, we have been very close to the true solution. Okay, so the answer is if you can introduce a acceleration factor by making that factor bigger than 1, you will be able to accelerate this process. Any question? Right. Okay, so second question, how to find all rules? That's a typo. So let's visualize this function in a bigger picture. So it has one root at 4.0. This is the one we just found. Another one, which is a tangent point, which correspond to 2 equal roots at 1.0. Okay, and by starting the iteration at 2.0, we're able to finally find the root at 4.0, but it doesn't find the other root at 1.0. So how to find the other 2 roots? So let's try a different way of iteration. Let's start from here, from some value bigger than 6. Okay, so we follow the same procedure. We first draw a vertical line up, so we intersect with this blue curve at this point. The second step, we draw a horizontal line, intersect with the straight line at that point. Then that's finish the first iteration. The second iteration, we go up, then horizontally here. Okay, so after 2 iterations, we get to a point close to that root. So if you continue, basically you will converge to the same root of 4.0. So if you try other initial estimate, you will find out. So there's some area which like a domain of attraction. So once you get into that domain, you will never escape from that domain. So you will converge to that root, like 4.0 roots. So this is the domain of attraction for that root. So when you draw this vertical line, horizontal line, which is like the trajectory of the algorithm finding the solution. If that trajectory is get into this domain of traction, it will stay there. It will converge to that solution. Okay, so what if we start slightly different from another estimate? It's still very close to 6, but you see it's just slightly smaller in the first case. So if we go up and go to the left, go up, and eventually it get to the other two roots at 1.0. So which means there's another domain of traction shown by this green rectangular area. So once you get into that region, you'll stay there. So which means different root of the equation may have different domain of traction. If you're able to get into that domain of traction, you will convert to that root. Okay, so to answer this question, how to find all roots, you just try many different initial estimates. But how many to try, we don't know, unless you have big picture about this this function. But from here, we also know to get to either of the two rules, two solutions, you need to be able to enter either domain of traction, right? So what if you fail to enter any of the either solution? So what happened? The process will diverge, which means you cannot find any root. Okay, so the question, the answer to this question will be no, it's not always convergent. So now let's try a third initial estimate. You see, this initial estimate is also very close to the first two. We just slightly move to the right. Let's see what happened. They go up, go to the left, go up to the right, and they keep iterating. It will never enter, never be able to enter any of the domain of traction. So it will diverge. Okay. All right. So that's the answer of the questions number 2 and 3. So any question here? Is this very clear? Yeah. So which means the initial estimate of the solution is very important. The last question. So is there any alternative way to write the iteration formula? Basically, we mean the GX, which carry all the nonlinear information of the original equation. So see what we did to transform the FS to GS. So we actually move this GS because we want to have a left-hand side to have a single S, right? Right-hand side the rest of the nonlinearity. So it's very natural we move this linear term to the left, then divide both sides by 9. So we have this formula. But you may think there could be many other ways to write this formula, because the goal is to have a single S on the left and everything else will be on the right. So what if we do, instead of moving the entire 9S to the left, we only just move a single S. So we split this one to the 8x plus x, right? We only just move this single S to the left. Okay, then divide both sides by -1. So it will give you this second formula. They also meet the same requirement. So which means we can use this second formula to iterate. Okay, yeah, the right-hand side still keep the third order nonlinearity. Let's see what happened. So the blue curve is the original one we use, and this green curve is the new alternative formula. It's still the third order nonlinear. But you see the shape of the curve is like it's become narrow. It's just like push from both sides to make it shrink. So which means domain of traction also change. So this green and the red regions indicate the domain of tractions of the original formula, which means there's a so if we start iterate, okay, within this area, this domain of traction, or we are able to get into this area. So you'll be safe to track, to convert to either of the solutions. But for the second formula, the both domain of traction become smaller. So which means in order to convert to the solution, you need to be sure to enter this smaller domain of traction. So answer is the second formula is more difficult to convert. Yeah. So how do we know which formula is better, which is worse? There's no general principle. You have to first you need to know the type of nonlinearity of your formula, and also you need to utilize some experience or the field knowledge, domain knowledge to help you to determine the right way to iterate. We'll talk about that when we move to the power flow equations. Okay, so this is the general ideas and the discussion about the Gauss-Seidel method. So now we're ready to move to power flow equation. So if you want to use Gauss-Seidel method to solve power flows, which is not it's just single equation, right? Which is the list of equation. If you have n buses, we have n equations. And if here we talk about the real equations, we have a 2n real equation. Okay, so each equation may be like this one. So if we move everything to the left, then right will be 0. So each equation need to be whole. So to start iterate, we need to rewrite each equation. So we move one variable to be solved to the left-hand side, and the rest of the equation will be on the right-hand side. Then we'll start the iterate. We start from x0 as the initial estimation. Then we utilize it, plug in those initial estimate to the right-hand side. We get the result from first iteration. We keep doing this. Okay. For instance, after k+1 iteration, we have the value of x, and then we check the update compared to the value from previous iteration. So if that update is small enough, so we'll stop here. Then we can just take the value at case iteration as our final solution. Okay, so that's the idea of Gauss-Seidel method. Let's see what equations we have. We start from this power flow equation. Okay. We can rewrite the equation. We multiply both sides by the denominator, so we'll have this one. So this equation, the real part will tell you how to calculate P. Imaginary part will tell you how to calculate Q. The first equation can be transformed into this form. Okay, so what we did is we first move this item to the right, and on the right hand side, and we will move this VI to the left, right, by dividing both sides by the YI. So we'll have this formula. We just did a very small change on this equation. So I intentionally color those notations. Any black one means they're constant. They remain constant and change during this entire solution process. Blue values means their value of the current iteration. The red value means the value to the next iteration. Okay, so at each step, at iteration k or k+1, we use the old value plug into those places as the blue variable, and we calculate the right one. And then we'll give the right to the blue again. Then that finish one iteration. So the first equation is good to calculate the voltage phasors, right? From a second equation, we split into a two. One is on the real part, the other on the imaginary part. So real part, we can calculate the P, and the imaginary part, we can calculate Q. So similarly, anything in black means constant. Blue means the value from the previous iteration, and red means the value of this new iteration. we have 3 types of buses to be calculated. Each bus need to assume 2 values already known, and the other 2 to be solved. Okay, so for the PQ buses, we need to find the voltage, magnitude, and angle. For PV buses, we need to find Q and angle. For slide bus, we need to know P and Q. Then what iteration formula we have will be those 3. So we just pick maybe 2 of them, or maybe 1 of them to help us to calculate the value we want. Like for instance, for PQ buses, we only need the first formula, because the first formula gave you the voltage phasor. So each time you use this formula, it will give you a new voltage phasor. So when the iterations stop, this value will be the final answer for the voltage angle. Okay, so for PQ bus, we only need formula number 1. For PV buses, PV buses we know P and voltage magnitude, but we don't know angle. We still need to utilize formula number 1. But for the formula 1, we don't use the voltage magnitude because voltage magnitude already given. So we only need angle information from the first formula at each iteration. Next, for the PV buses, we also need to know Q. So Q will need to utilize the second formula about Q. Slide bus, we need to know both P and Q. So we're going to use formula 2 and 3. Okay. So in the next slides, we're going to go into each type of buses to talk about how to use that 1 or 2 corresponding formula to do the iteration. Let's talk about the first type, PQ buses. So PQ buses, this is our standard Gauss-Seidel method algorithm. And here, what we're going to solve for S will be voltage, magnitude, and angle. And we only need to utilize the first formula, which is this one. And for PQ buses, P and Q are already known or scheduled. For instance, if this bus is a load bus, P and Q can be estimated based on the load forecasting. If there's a bus which has a generation, for example, the generation doesn't change the voltage, but it will provide the P, the IT power, and also reactive power at constant power factor. So they can all be also considered as PQ buses. So here we just take the P as scheduled value. So this scheduled value will be determined in the next section when we talk about the generation dispatch, right? That's in the generation dispatch is just going to solve a more general power flow analysis problem. So you have some room to adjust between the lower limit and upper limit for each generation. So by that section, we'll be able to know the scheduled value for each generator. But in this section, in power flow analysis, we assume the PQ already know that for the load. Okay, so how do we determine the initial gas? Under normal operating conditions, we know the slide bus. You may be able to know the slide bus magnitude and angle. A slide bus means a very large system, which basically just the equivalent of a very large system. It could be your neighbors. For instance, if you're operating like a smaller region connected to a much bigger system, so you can treat that big system as the equivalent bus. For that equivalent bus, the voltage usually will be very close to a nominal value, right? 1. And you can use the whatever angle for that system as 0 as a reference, because when you define a phasor, you can make any angle be your reference. So you make your large neighbor as the reference. So that bus can be treated to have the voltage phasor 1 all the time. For other buses in your system, if it's a generator buses, usually the angle need to be bigger than the slide bus, slightly bigger, because in order to deliver active power from one area to another area, you need to have increased angle. So which means the generator buses will have relatively higher angle compared to load buses. So if we assume the slide bus to be 0, which is like a mean value of the angle, so generator buses need to have slightly higher angle than 0, or higher than the slide bus angle. And load buses can have a slightly lower angle. Like for instance, to determine a good initial estimate for any generator bus, I make the initial angle to be maybe 5 degree, 10 degree, whatever. For the load buses, which is the PQ buses, we need to know the initial estimate. So we can take maybe the angle slightly negative, okay, and the voltage slightly lower than 1. Yeah, that's up to you. But if you don't want to utilize that assumption, you can just simply let any initial phasor for each PQ bus as simply 1, same as slide bus, unless you have a better, you have strong reason to make a better estimate. Yeah, this is everything we need to know about PQ bus, because there's just single formula. You just iterate using this formula. The second type is a PV bus. For PV buses, we know P and the voltage magnitude. We need to determine the voltage angle and also rated power. Okay. So PV buses are generators. So as I said, the P will be a schedule based on the generation dispatch. And voltage can be specified based on like voltage regulation. So we need to start from some initial estimate. So you need to give some initial angle. From previous slides, you can make this initial angle be slightly positive. And the voltage, because the voltage magnitude already given, right? So we use the initial angle together with the magnitude, we determine the initial voltage phasor. The formulas we need will be the one formula for Q, the other formula for V. But keep in mind here, we don't need to know the voltage phasor, we only just need to know the angle. So when you use the first formula to iterate, it gave you the voltage phasor, but we only need angle information. We don't need the voltage magnitude. The voltage magnitude already given. We cannot change that value. So how do we update the angle based on this calculation? Okay, so which means we can, one thing to do it, we only take the imaginary part. If we update both real part and imaginary part, you actually change the magnitude, but we only keep the imaginary part. And then from the imaginary part, also using the given the magnitude, we calculate the real part. Then we form the new phasors by using the real part and the updated imaginary part to get the updated value for the voltage phasor. Okay, so here we take one more step calculation. We didn't directly utilize whatever from the iteration formula. We only take the imaginary part and we try to keep the absolute value same to calculate the real part. The real part depends on the imaginary part, and then we get the updated value. Okay, to visualize what happened here, if from iteration K, we have this voltage phasor, and the voltage magnitude is already determined, right? Because it's a PV bus. So we can only update along this circle. We cannot leave this circle. But based on the iteration formula tell, we need to change the voltage phasor to this one, which you see is longer than the radius of the circle. So we only just get the imaginary part. And using this imaginary part, we actually, it's like we move the head of the arrow along this horizontal line to keep the same imaginary part until we have this right facer, which is stay on the circle. So that will be the new value. So we'll keep this value. All right. So we keep the iteration until both real part, imaginary part less than the error tolerance. Then we'll just stop there. If you want to use an acceleration factor, for instance, bigger than 1, this is where you need to plug in, right? You need to add the factor here. So that can speed up the iteration. Okay, so let's stop here. We'll continue on Friday.